starting. All attendees are in listen-only mode.
Hi, good afternoon all. Welcome to today's session, wherein we will be discussing about CAD techniques, building and importing geometries. Um, as all of you have already attended yesterday's session, I would still be going through few details about the session itself. That all the attendees will be on mute during the entire session, and we will start this. We will be starting the lecture session at 3 o'clock on all days. If you are having any questions, comments, if you are not clear about any steps, please type them in the questions tab that you are having, and me or my colleagues who are available today as moderators, they will help you with your queries. If you are having any questions unanswered, then please join us tomorrow for Q&A session at 3 o'clock, 3 p.m. IST. And after the session is over, like Monday's session, we will also be discussing the assignment, and those assignments will have to be submitted by 2 p.m. IST tomorrow. The recording of the session will also be available for a week, and for today's recording will be shared with you after the session is over within 2 hours. Details about the assignments as well as the link for the today's recording will be shared with you after the session is over. We will also share the passkey which will be required to open the assignments. Next is in order to download and submit the assignments, you need to log into COMSOL server, as my colleague Uttam had already shown you during the day one session itself. And for each day, you will be given one new passkey in order to unlock the assignments, to see the assignment questions, as well as to upload your solved models as well. So with this, we will begin with today's session, that is day 2 CAD technique. We will be discussing about the CAD techniques. So the agenda for today's session is, first of all, we will be discussing about geometry modeling concepts. Then how you can work with geometry sequences in COMSOL, various geometry operations available in COMSOL, then a few details about the CAD import functionality available in COMSOL, what kind of files that you can import in COMSOL, and what kind of operations are allowed in order to work work on those models in COMSOL. During the entire session, we will also be discussing various tips for successful geometry building as well. Then also we will be discussing about defeaturing and repair operations, especially for the imported geometries. And towards the end of the session, we will also be having one hands-on session wherein you can build the geometry from scratch along with me. During the entire session, whenever you are having any questions, please feel free to type them in the questions tab that you are having. We'll be happy to answer them. So as you already must have received these CLC video links, we will be just quickly go through those what was discussed during those COMSOL Learning Center videos on geometry. So you must have also listened to this how you can create 2D geometries in COMSOL, and from 2D how you can get 3D geometries, like it could be extrude operation, it could be revolve operations, and so that you must have seen. A part of that geometry creation was also discussed during day one session as well. So here in this case, with creating 2D, you must have seen various options, like how you can use parameters, different transform operations like copy, mirror, array, etc. Or when you are working from 2D to 3D, then how you can have 3D components, how you can work in 2D space dimension while you are dealing with a 3D geometry. That is how you can create a planar geometry first, and from that how you can get a 3D object, like by using extrude operations, and so. You also must have seen this, how you can import geometries, how geometry sequence is handled in COMSOL. We will be looking into this few details briefly in today's presentation as well. Also, the COMSOL Learning Center videos also talk about various primitives, like 2D primitives as well as 3D primitives, and different geometric operations in order to get the complex geometry out of that. The one important aspect that was discussed in Learning Center video was finalizing the geometry. In today's session, we will also be discussing a bit about how what do we mean by finalizing geometry options and how and why they are important while dealing with various analysis. So as you might already be bit aware of our COMSOL product suite. So with COMSOL, you get first of all access to COMSOL base package, with which you get graphical user interface, which is common to all the applications, be it electromagnetics, fluid, heat transfer, structural, chemical, anything. Apart from that, you also get access to various basic CAD building techniques available with base package, meshing techniques, post-processing techniques, and few physics interfaces, and some built-in materials as well. In addition to that, if you want to go for any other application-specific modules, you can select one of the add-on modules that are listed over here. In today's session, we are not going to focus upon any of these modules. Our today's focus is going to be how you can use COMSOL's built-in functionality in order to create CAD files, as well as you can see over here that we also have something called as interfacing products, wherein by using various options given over here, either you can import finalized CADs from other software, or you can have a bidirectional coupling between COMSOL and other CAD tool which are listed over here, for which Livelink product have been mentioned. So we will be discussing a bit about that as well, how you can import the finalized CADs and how you can make them usable for further modeling requirement. Just a second. Yeah. So let's look into geometry modeling concepts in detail. So while getting geometry into COMSOL, there are various options available. First of all, you can create geometry using COMSOL's native CAD tool, wherein as discussed in COMSOL Learning Center video, as well as few details that we'll be discussing today as well, you will be getting access to various 2D and 3D primitives, as well as some 1D options as well. So by using all those options, you can create geometry in COMSOL, or you can import finalized geometry from other softwares into COMSOL as well. That is also possible. But the difference between the point 1 and point 2 is that whenever you are importing finalized geometry from other softwares into COMSOL, you do not get access to all the steps or the steps required or used to build that geometry in other software. Whereas when you are creating the geometry in COMSOL, definitely you get access to all the steps. So here just the finalized geometry will be imported. There is a third option, that is insert sequence, that is from the other COMSOL model file. For example, you might have built one COMSOL model file, that is .mph file, wherein physics and everything has been set up. Let's say today you are solving for electromagnetics analysis, and later you want to solve for some other physics altogether, let's say structural mechanics or so. And in that case, you want to use the same CAD file or the same CAD what you have used for that electromagnetics analysis. In that case, you do not have to create that geometry file again from scratch. What you can do is you can just launch new COMSOL instance and then use this insert sequence option. And from that insert sequence option, you can select this MPH file through that insert sequence, and whatever the modeling steps, whatever the geometry building steps that were used to create that CAD, all the steps will get imported. That is, the entire sequence will get inserted into a new COMSOL file as well. So these are the basic three options I can say. The fourth option, as I was discussing earlier, it could be that the Livelink for any CAD tool, that is wherein you will be having bidirectional linking between COMSOL and the other CAD tool. So while dealing with all these different geometry options, the kernels will be used based upon the models that you are having. But what do we mean by kernel? What do you mean by geometric kernels? So the geometric kernels are nothing but the software components that handles the geometry. Means how COMSOL will see the geometry will be based upon how this what kernels that you are using. So with the base package, if you are not having access to any add-on license, like if you do not have access to CAD import module or design module or any live link or any different CAD products, in that case, the default kernel that we'll be having is the COMSOL kernel. And if you are having any other CAD module licenses, as I was mentioning earlier, you will be having access to this CAD import module kernel as well. So these geometric kernels, they can keep a track of the mathematical representation of the objects. It has also different functions in order to construct objects, as well as how these objects are interacting with each other. Because based upon that, it will decide that how the finalized geometry or the finalized CAD will be represented. And the geometric kernels will be, means they have one important role, that is they ensure that the geometry is associative. That means settings are kept intact after the modifications are done. Just for the example, you are having some two squares that you have added already, and after that adding those two squares, you want to add one more square between these two squares, that is square one has been added, then you have added square two. Before building the square two, in between, if you just want to insert one more modeling object itself, in that case, while modifying the sequence, the associativity will be maintained by these geometric kernels. So as I was mentioning, we have two kernels, that is COMSOL kernel, which works best with the geometries created in COMSOL software. The next one is the CAD import module kernel, which is available with CAD import module or design module or any live link products for CAD. If you are having access to any one of these licenses, you will get access to this CAD import module kernel as well. And this is essentially a parasolid kernel, which you get access with CAD import module. So now when we are talking about this, how you can create geometries or get geometries in COMSOL, or how to represent the geometries, or how the geometries are being represented by means of this geometric kernel. Now let's look into geometric objects and entities in 3D itself. So when we are starting in 3D, you must have seen on Monday's session that, or the very first session, that you need to have different domains, different boundaries, edges, points, etc. In your model in order to assign various types of conditions. But what do we mean by domain, boundary, edge, or point? Because you can work in 3D modeling environment, 2D modeling environment, 1D modeling environment as well. So let's see how to understand that. So to start with, when we are working in 3D, the volumetric entity will be considered as domain. The surface level entities will be considered as boundary, and edge and point will be having the usual meaning. If you are working in 2D modeling environment, then in that case, the surfaces will be considered as domains and the edges will be considered as boundaries. So in general saying, whenever you are working in any space dimension, the highest dimension that you are working with will be considered as domain, and the subsequent ones will be considered as boundaries. So for example, in 3D space dimension, the volumetric or the 3D space itself is the highest dimension, and hence volumetric entities are considered as domain. And the next level is 2D, that is the surface, and in that case the surfaces will be considered as boundaries. So whereas if you are working in 2D environment, the highest dimension is 2D, and in that case the surfaces will be considered as domains and the edges will be considered as boundaries. Now if you are working on 1D environment, in that case the edge will be, that is the 1D element is the highest dimension, and hence that will be considered as domain, and the endpoints of that edge elements will be considered as boundaries. Going down 0D, it is definitely space independent, and over there definitely we will not be having any geometric entity level. Moving forward, let's look into how you can create geometry for analysis. So in COMSOL multiphysics, you can use solid modeling or boundary modeling as well to create 1D, 2D or 3D objects. So what do we mean by that? So if this is a 3D object that you are having, then you can have a surface or you can have a edge also. And all these different objects, if you are working in 3D, this is a solid object. If you are working in 2D, this is a solid object. If you are working in 1D, this is a solid object. Now, the solid modeling is a geometry which is formed as a combination of solid objects using Boolean operations. So what do we mean by that? When you are working in 2D, let's say you have created two surfaces and those two surfaces are nothing but the solid objects, and when you convert or when you operate, use different Boolean operations on them, you will be having resultant solid object. Whereas if you are talking about the boundary modeling, that is, you will be creating a solid out of the boundary. Means, for example, if this is the kind of closed curve, if you are having, from that closed curve, you can create a solid object. That is, you can create a surface, solid surface from that closed curve. So this kind of modeling is also possible in COMSOL. Next is you can also have combined objects, that is in 3D space dimension or 3D environment, you can have just 2D surfaces as well. And for example, as you can see over here, this is one sphere. In that sphere, we are having just one boundary. The example of this could be like, for example, if you are solving some electromagnetics analysis, and that electromagnetic analysis, you might be having some thin conducting surfaces. But in order to have any electromagnetic field, you will need to model air around that conducting surface itself. And in that case, you can see that this is the complete 3D solid object, and in that we are having a surface. So such kind of combined modeling is also required, and that can be done in COMSOL. So in those cases, you can embed 2D objects into a 3D geometry. Now, while talking about these different 1D, 2D and 3D geometry to start with, let's look into few techniques for creating geometries. Whenever you are creating any geometry, whenever you are creating any model, always ensure that, or always see that how you can simplify the model in order to reduce the computational efforts, as well as have the maximum computational efficiency from your model. So one of the popular techniques that people use is that using symmetries. So whenever you want to reduce your model using symmetries, you need to always see that whether the model that I am considering, whether it is symmetric from the geometric point of view, as well as it is symmetric from the physics point of view as well. Means, what do I mean by that? Just for an example, this is a cylinder that we are having. Okay. Now in this cylinder, if we just consider the geometric symmetry, you will see that it can be very well represented by its 2D axis symmetric cross section. That is, if we just take a cross section, that is 2D axis symmetric cross section, this is the rectangle, and if we revolve that rectangle around the axis of symmetry, we will end up with cylinder itself. So definitely the geometric symmetry is indeed present in this particular object. Now, what do I mean by physics symmetry? So case one I can say is that let's say you are solving for the heat transfer analysis. Okay. And in that heat transfer analysis, in that heat transfer analysis, you can say that this top surface that you are having over here, you are applying some temperature T1, let's say, and the bottom surface that we are having over here, here in this case, we are applying some temperature, let's say T dash or T2. So two different temperatures are applied. And in that case, we just want to see that how the temperature gradient along the height of the cylinder. So in this case, if we just try and represent this entire model with this 2D axis symmetric environment, we can see that this still T1 will be applicable on this top boundary. This T dash will be applicable on this bottom boundary. And even when we are revolving this entire rectangle, this T1 and T dash will still be intact. So in this case, the model is symmetric from the physics as well as from the geometry point of view. Now let's see the next case, that the geometry is definitely symmetric. Let's say we are having a small patch over here, okay? And that patch we are having some, I can say this patch that has been added over here. okay, on one surface itself. Now in that case, do you think that this model can be represented by 2D axis symmetric space dimension? You can just type in your replies that whether this model can be represented by 2D axis symmetric in 2D axis symmetry or not. And this particular patch is having some temperature as T3. So that's the condition that I am providing. So T1, T2, for T1, T dash that we are having is the conditions are already given there. And let's say this is the T3 temperature that I am providing on that small patch. So the geometry still remains the same over here, but you can see that I'm just applying some arbitrary temperature at one of the patches, one of the patch that I have drawn. So will this allow me to get this model in 2D axis symmetry? Okay, interesting answers. Means it is a mix of yes, no, and someone have mentioned that you can model it in 2D. There is also one interesting reply that we need to change the line of symmetry. Okay. Yeah, so many means most of you have given the right answer. This cannot be approximated as 2D axis symmetry as well as, because even though if you change the line of symmetry, right, none of the symmetry lines will allow you to rotate and get the entire object, because this particular patch is available at one section itself. So this particular problem is quite a symmetric problem, and in that case you cannot have symmetry used over here. But whenever you are going for such problems, or whenever you are having any problem in hand, before starting to draw any geometry, you should always ensure that or you should always check that whether any symmetry is possible or not. Then you can also make the geometry match the boundary conditions as well. Means whatever the boundary conditions that you need to apply, whether those boundaries are already present in your geometry or not. If not, how to get them, get that partitioning done in order to apply those boundary conditions. Next is you should always ensure that you are avoiding excessive details. So for example, if this is the geometry that we are importing, and some CAD designer might have created this wonderful geometry, but as you can see that from the modeling, mathematical modeling point of view, this airflow and these whatever the words which are written over here, definitely they are not important. But at the same time, as you are just importing this geometry as is and using that geometry as is, at the meshing level, COMSOL will see that, or any software for that matter will see that, okay, all these fine details also need to be meshed with really very fine mesh elements. And with that, unnecessarily, your problem size will increase. And in that case, you can see that this you do not have to resolve these small details at all. They are not important from the modeling point of view. So whenever you see such kind of details, before getting those geometries into COMSOL, remove them, or you can remove them after you have imported into COMSOL by using various defeaturing techniques what we are having in COMSOL. If you are creating geometries in COMSOL, always ensure that unnecessary details are not included in the geometry wherein which are not required from the modeling point of view. So let's look into then how you can choose the right space dimension as well. So COMSOL supports modeling in not space dimension, I would say 0D, that is the space independent, wherein you can solve various types of lump circuit, be it thermal lump circuit, electrical lump circuit, or the mechanical circuits. But when we are talking about the space dependent models, you can have 1D, 1D axis symmetric, 2D, 2D axis symmetric, and up to 3D also. So what do we mean by 1D? So 1D is nothing but the model which is representing some 2D or 3D geometry under the assumption that nothing is changing in other rest of the dimensions. So if there isn't any variable changing in other directions, in that case you can have a 1D representation of the model. Whereas if it is a 1D axial symmetry, then in that case this straight line which is shown over here, the straight line which is shown over here is nothing but a model which represents a radial direction, and again it is actually symmetric. That is, when you are rotating this line about the axis of symmetry, you will end up having a surface, and with that you can say that this is the 1D axial variation, and the out of plane variation is not important over here. That is, nothing changes in the out of plane direction as well. Next is 2D dimension, that is no variation of the solution in one particular direction, or you can have influence of the finite extension of the third dimension neglected. So either of these two things, whenever it is possible, you can model a 2D problem. That is, for example, 2D assumptions example could be, if you are from the electromagnetics background, you can correlate it with current conservation equations, wherein one can solve in plane current conservation equations. But again, you will need to ensure that what kind of cross section that you are taking. Means, just for an example, if this is a COMSOL window, I will just draw one 3D object quickly. So let's say I'm having a block which is drawn over here. Now in this block, let's say if I am applying some potential on top of this boundary. If I am just applying some potential, non-zero potential over here, and then non-zero potential over here, in that case, I can afford to take cross section along YZ plane. But at the same time, if I try to take cross section which is parallel to XY plane, definitely the 2D representation of the problem will not be appropriate. And hence, even though we are saying that you can have this 2D modeling done for the current conservation equation as well, your model setup, not just the geometry, the physics boundary condition what you are applying should allow you to convert that model in 2D. If you are from the mechanical background, you can correlate it with plane strain or the plane stress conditions for the 2D stress analysis as well. For the 2D axis symmetric problem, we consider the RG plane, and this RG plane is nothing but, as we were discussing earlier, you should be able to get the complete 3D geometry if you revolve that surface which we are considering, and if that surface is revolved about the axis of symmetry. If you do that, if you are ending up with the actual 3D geometry, then in that case, you can represent it with the 2D axis symmetric problem. But again, over there as well, as I was mentioning, your boundary conditions, your physics conditions should allow you to approximate that problem with 2D or with 2D axis symmetric or 1D as well. When we are going, means if anything that modeling it with 1D, 2D, 2D axis symmetric, if it is not possible, definitely you can go ahead and build the problem in 3D. But in 3D also, check that if any type of symmetries are possible, that is half symmetry, sector symmetry, if they are possible, in that case, you can reduce your problem to the sector symmetry also and apply the appropriate boundary condition. The next good approach also could be, if you know the dependence in one direction, and in that case, you can represent that dependency in terms of some analytical function. So in such a cases, rather than modeling the entire 3D object, maybe you can represent that one directional dependence by using this analytical function as well. So just to recap about the first section, means how geometry is organized in COMSOL. We discussed about what do we mean by domain, boundary, edge, etc. And as I was mentioning, the geometric entities of the maximum dimensions are called domains, and while those of the next highest dimension are called boundaries. That is, in 3D, the maximum dimension is going to be 3D, and hence the volumes will be called as domains and the surfaces will be called as boundaries. Whereas when we are working in 2D environment, the maximum dimension is going to be 2D, and hence in 2D modeling environment, surfaces will be called as domains and edges will be called as boundaries. Going for 1D environment, the highest dimension or the maximum dimension is going to be 1D, and hence edge elements will be called as domains and the endpoints will be called as boundaries. So now let's look into how you can work with the geometry sequences as well. Yeah, let's look into how you can work with geometry sequences. So important note over here that whenever you are working with geometry, the unit is quite important. In COMSOL, there are two types of units to start with. For example, if you go to root node, over here, you will first of all see the unit system. By default, this is SI system. If you want, you can change it to any other system as well, that is British Engineering Units or CGS, etc. Different unit system that you can have. Now, this is for the global unit system that we are talking about. When we are going to geometry node, you can see the length units can be changed from here. Now, whatever the length unit that you are using over here will be used to create the geometry. But while solving the model or presenting the results, all the units, whatever, or all the dimensions which are used in your geometry, that will automatically get converted in terms of the global unit system that you have selected. Means, for example, in geometry, to start with, if you just start with inches itself, right? You can create your geometry in inches, that is a block or whatever the objects that you are creating. Once you apply the physics and once you solve it, you will see that internally while solving, entire these lengths will get converted into equivalent values in terms of the global units that we have selected over here. The next point, apart from these units, is that when you are having these units, there is one important option, that is scale values when changing the units. It may happen that you might start with a certain type of um, object that creating geometry, and later you may realize that okay, you want to change the units or you want to scale the values. So based upon what exactly you want to do, whether you want to scale or whether you simply want to change the units, you can select this option as well. And this option can be used very effectively also. Just for an example, I will show you that how you can use this option. For example, I am just starting with a new button itself. So this is 3D, and no, I do not want to change any physics. So once I just create geometry, let's say I'm just having meters as units and I'm just creating a block. At any point of time, you can just measure also. So I will just show you how you can measure it. So I'm just measuring this edge, which is 1 meter by 1 meter by 1 meter. Okay, to start with. Now let's see if I just go back to this geometry node and change the length unit to mm. And I will just click on build all. Now if I go back to block, you will see that it is showing 1 mm, and the same will be displayed if I am going to measure it. That if I just go and measure it, earlier the edge was represented as 1 meter. Now it is 1 mm that you can see. Now if I go back over here and if I just say that scale values while changing the units, and let's say if I just change it to meters, you must have seen that that asterisk started appearing over here, right? And here if I just click on build all, I can just click on zoom extend, and now I can measure what exactly is being shown. So here now you can see that it is changed to 0.001. Earlier it was 1 mm, and now when I changed it to meters itself, and then first I had selected scale values while changing the units, and hence even though it changed from mm to meter, you can see that the values are scaled and accordingly the unit has been set. So this is how you can use these scale values while changing the units checkbox effectively. So once the session is over, you can also try out this. Once you start with one by one cube, and if you keep this box selected, what kind of option that you get? If you keep that box cleared and change it to 1 mm, what kind of options that you can receive? While discussing about the geometry sequence, you must have noticed that few options which are appearing, like once that asterisk started appearing on that box and so. So what all these options actually mean? So the very first thing is that this is the geometry node, and all the steps which are used to create the geometry will appear over here. That is that all the geometry operations, the sequence will appear under the main geometry node itself. Whenever you see such kind of green box, that is the current node, and this is the form union, that is the finalization node. We will talk about that in later. Now there are different options. That is the first of all the asterisk. That is, this node has been edited but not rebuilt. So for example, just now we didn't change any settings per se inside that block feature itself, but we have changed the settings in the unit section. So when we are changing the units section per settings, the block settings are automatically getting updated, and hence it says that there are certain settings inside that particular node have got automatically updated and hence need to be rebuilt. Based upon that, means unless this circle 1 is built, the difference operation is using circle 1 and circle 2, and hence the nodes which are dependent upon the previous operations which needs to be rebuilt, they will be shown as orange node. That is, there isn't any direct changes done in this particular node, that orange triangle node, but the entities which are being used in this particular node are being edited, and that first of all we need to build that particular node, and based upon that updated node, the difference node will also get built again. This is the current node, as I was mentioning earlier. And whenever you see any grayed out nodes, either they could be the disabled nodes, or if they haven't, they are not disabled, these are the nodes which are not built yet. Yeah, I will just take a couple of questions at this point. The very first question, that is it possible to create parametric geometry? If yes, how? Yes, you can create parametric geometry. While setting up the creating the geometry itself, right? Means what I was showing earlier here. So rather than directly providing a value, I can just directly provide L, then maybe here D and H I can provide. And rather than providing the fixed values, I can just provide those values over here, 1M, or then same way it is D. I can mention as 1 meter, and W I can just mention as, let's say, 2 meters or so. Now, when you create these geometry parameters over here, LDH, sorry, not W. When you create such parameters, then whenever you are updating this parameters value over here, automatically the geometry will get updated. Additionally, the H means for the rest of the parameters also can be a function of the previously defined parameters as well. So for example, I can just mention as 2L also. And in that case, whenever I am just changing the L value, the entire geometry will also get updated. It could be like 10 if I am just doing, or let's say 2 if I am doing, putting the value as 2, you can see that the entire geometry is getting updated. So this way you can parameterize. In today's hands-on, we will also get to see that how this parameterization can be used effectively. Yeah. Okay. Yeah. So now let's moving on. Let's look into these geometric sequences as well. So you need to click on the node in model builder window to access or modify the settings. So as you might have noticed over here, I need to click on the, if I am just having 2 blocks, in order to edit the settings of each node, I just need to click on that particular node. Corresponding settings will appear in the settings window itself. You can also enable or disable the geometric operations in your sequence. So sometimes it may happen that you might have added some operations and later you realize that that operation is no longer needed. In that case, you can altogether delete it or you can disable that option as well. It also supports the geometry sequence, also supports the geometry operations on imported CAD geometries. Like for example, you have imported the CAD and after that you might want to remove some excessive details, or if you want to partition that geometry, all those things are also possible for the imported CAD. Whereas if you are using these live link interfaces, in that case, one can get access to the entire geometry sequence through the through live link, and you can access that geometry sequence from the parent CAD software as well. And here in this case, you can have fully parameterized geometries. As of now, I have just shown you that how to create that block, but you can create very complex geometries wherein the various parameters are defined to start with, and any geometric entity or the image geometric dimensions that you are defining in your geometry sequence could be a function of any different parameters also. So fully parameterized geometries are also possible. Now let's look into the important concept for today, that is the geometry finalization. Yeah, there is one question. Is it possible to parameterize the process building geometry? For example, if I want to add same geometry multiple times, can I parameterize this process? Yes, you can parameterize this process as well. Means basically you want to say that how I can repeat the same sequence again and again. One thing is that you can copy paste the sequence. That is also possible. Another option is, just a second. So one option is you can duplicate it, or you can copy that particular feature also, and you can directly paste that feature as well. Or else once you have created you can paste that feature, or there is something called as this developer tab is also available. This is little advanced, but here in this case we are having some COMSOL blogs. I would request my colleagues colleague Uttam, who can share those blogs with you, how you can automate the processes in COMSOL model building processes. By using this developer tab, you can actually record a code to create a certain geometry part. That is, you might be having some 10 different steps in order to create one particular part, and you want to repeat that sequence again and again. In that case, one can just record a code of that particular sequence, and by then once that code is recorded, you can just run that code, run that method in order to get that code executed again and again and again. So such kind of things can be automated. My colleague will shortly share that blog with you all. Okay, so moving on, let's look into this geometry finalization. So the geometry finalization determines how to form the geometry that is used for meshing and analysis. This is essentially how COMSOL interprets the geometry or the how COMSOL interprets the geometry that you have created. Means what kind of domains, boundaries, etc. that it can see for the further analysis. One thing is that whenever you are working on the axis symmetric model, even though the entire geometry has been created for r equal to r less than as well as greater than 0 plane, complete plane, at the finalization level, all the parts which are present at r less than 0 plane will be removed. Just r greater than 0 plane will only be considered, because the that is the axis of symmetry that we consider. Now, in the finalization method, there are two different options available: form union and form and assembly. What do we mean by that? So with form union, which is a default option by the way, it forms a union of all the geometry objects that you have used. So let's say you are having a circle 1 and circle 2. These are the two geometry objects that you have used. Now When you are going for the finalization, in that case, after the finalization is done, it will divide this entire geometry into three parts, that is domain 1, domain 2 and domain 3. The overlapping part over here, which is common to both the circles, will be identified as a separate domain altogether. The one of the key points for the form union is also that whatever the field variables that you are solving for, whatever the physics interface that you are solving for for that, the field variables will be continuous across these internal boundaries. These boundaries will be considered as internal boundaries because of the finalization method that we have used. And along that internal boundaries, the field continuity will be by default maintained. Then at the same time, it will also ensure the mesh conformity. For example, as you can see over here, we are having a mesh in domain 1 and domain 2. But at the interface, at the internal boundary, the nodes are matching over here. So when you are using this form union, the mesh nodes will match. Now let's look into what do we mean by form assembly. So with form assembly, it will be treating as a collection of disconnected domains. So for example, if you are starting with the same two circles, but rather than using form union, if you do form an assembly, that option if you select, you will see that you will end up having domain 1 and domain 2. COMSOL will not recognize the overlapping or the common part, which is the part which is common to domain 1 as well as domain 2. It will just consider that these are like two just overlapping objects and they are not at all touching to each other. Means you can just visualize it as like you are having a circle which is kept at one plane equal, which is z equal to 0 plane, and the other circle which is drawn at z equal to 1 plane. So such kind of objects are drawn and these are not connected to each other at all, and hence as they are not connected to each other, the boundaries that you can see over here, right, they are not the internal boundaries, those are the external boundaries only. And hence as those are the external boundaries, as these circles, as these objects are not connected to each other, you will see that the mesh conformity is not maintained over here. That means you can have mesh independently done for domain 1 and independently done for domain 2, and the part which is means which appears to be common for circle 1 and circle 2 will get meshed separately from the domain 1's point of view and from the domain 2's point of view. Another thing to notice for form assembly is that these boundaries are not common between these two domains. That means the field continuity will not be maintained. And whenever you are using this form assembly, the extra step that needs to be done is that by default, while creating the form assembly, it will ask you whether the identity pairs should be created or not. Identity pairs are nothing but whatever the boundaries which you can see over here, whether you want to make the field variables continuous across those boundaries or not. And for that, first of all, you need to create identity pairs and then enforce that continuity under the physics interface itself. Another point is also with form assembly is that when you are using this form union, right, the internal boundary will be having one constant number only. That is, there will be just one identifier given for each boundary, which you can see over here. Whereas when we are using form assembly, the boundaries which are like of the overlapping region will be having two different or the different identifiers based upon which two domains are interacting through those boundaries. For example, the boundary that you can see over here, the boundary that you can see, this boundary, right? So this boundary will be having different identifier, the number from the domain 2 point of view and the different number from domain 1 point of view. And under identity pair, that's what COMSOL will do, that just create identity, that is, this is the identical boundary, even though they are having two different boundary numbers. So once you create that identity pair, you need to apply that continuity boundary condition. Creating identity pairs, you do not have to do manually. I'm just explaining that how it works internally. COMSOL, while creating this form assembly, COMSOL will take care of creating those identity pairs. So whichever the boundaries, wherever you want to enforce that continuity, you can include those identity pairs under the continuity boundary condition. So the next question may arise in your mind, that why do we need to have this form assembly in the first place? Because essentially, if we are enforcing some continuity across some boundary, then why don't we go directly with the form union only? Why to go with form assembly? Well, there are certain physics areas wherein the form assembly will be required. Means whenever you want to model any relative motion between domains, right? It could be sliding motion, it could be rotating motion. In such a cases, this form assembly will be required. And in those cases, one can have different type of meshing at if you are having some rotor type, means basically generator type of device, for example, if you are designing, then one can have different type of mesh at generator rotor side, one type of mesh at the stator side as well. Another advantage or another scenario wherein this form assembly can be used could be like if you are working on very complex geometry, okay, and then getting a really very good mesh for all the domains, it may become difficult, because as you can see over here, when we are using form union, it will always ensure that across this internal boundary, you are having the exactly the same mesh nodes, and accordingly the mesh will grow on either sides. Now, if you are having a complex geometry, in that case, it may happen that creating such kind of mesh might be quite difficult. And in those cases, you can have a form assembly, create mesh independently for the domains which are appearing to be overlapping on one another. And once you create this form assembly, create the mesh as you want to have, just use a continuity boundary condition in whatever the physics that you are using. And under that continuity, you can apply the identity pairs as well. So there are various uses of where you can use this form assembly method as well, the finalization method. So just to recap about this section, that is, we have seen geometry sequence wherein you can have many geometric objects, different operations, and what do these mean, whether you have rebuild that, whether you need to rebuild the operation, whether certain operations are dependent upon any other parameters, or certain objects can be disabled, deleted, all these options that we have seen. You can also have one objects with several domains. We have seen different two methods for uniting the objects also, that is form union and form assembly. Another option, or the one important point that I missed to mention, that we were discussing about, this is like domain 1, domain 2, etc. But many times people also get confused, that means how do we assign these domain numbers, or do we need to really assign these domain numbers? Well, when you are doing this finalization, right, at the finalization level, as we were discussing here, that it determines how to form the geometry, or how the geometry objects are also going to interact. And in that case, first it will see that when you are finalizing the geometry, the point which is closest to the origin will be numbered as 1. Means it will just try first of all getting the distance for all the points which are present in your geometry, and the point which is closest to the origin will be numbered as 1. And from there, it will start numbering 1, 2, the next closest point as number 2, the next closest point as number 3, so on and so forth. Once all the points are numbered, then after that, it will see that what are the edges which are having or which consist of smallest number of points. That is the edges wherein the points which are included in that particular edge are numbered with the smallest point. And from that, first of all, it will number the edge number 1, then edge number 2, edge number 3, etc. Then from those, once the edges are numbered, it will see that what are the surfaces which are associated with the lowest number of lowest number of edges, and accordingly the surfaces or the boundaries will be numbered. And later, lastly, the domains will be numbered, the domains which are associated with the lowest number of surfaces. And hence, like this, COMSOL will be deciding which is the domain number 1, domain number 2, domain number 3 as well. Because here in this case, one can easily say that this is domain number 1, and this could be domain number 2, and this is the last domain. One can decide to have a domain number 3. But if you see, means from the logic that I was explaining, if you are having the point, if this is the origin that you are having somewhere over here, in that case, this domain will be having number as 1, the overlapping domain will be numbered as 2, and the farthest domain will be numbered as 3. This is how the domain numbers are shown in, or done in COMSOL. So with this, I will launch the very first poll question just to get a feedback from your side that whatever the points that we have been discussing so far, if you are in along with me or not. So let's say, just listen carefully. Let's say if you are having a rod with length as 1 micrometer, okay? That is first you are opening COMSOL. In COMSOL units, that is the geometry units, is given as micrometers, and then you are just drawing one cylinder, let's say, and in that cylinder, the cylinder height that we are considering it as 1 micrometer, and radius whatever of your choice that you can consider. Now if I want to change that length from 1 micrometer to let's say 1000 meters, what are the steps that I would need to take? Means, in order to change it to 1000 meter, first build geometry with micron unit, and once the geometry is built, which option should I do? That is, change units to meter and rebuild. Whether it will directly change it to 1 micron to 1000 meter? Definitely not. That the first option is definitely ruled out. Now the next option is select that scale values while changing the units, that checkbox, and then change units to meter and rebuild it. Will it give 1000 meters? Please think about it. And there are two other different options given. That is, first of all, you need to select that checkbox, then change the units to nanometer, rebuild that cylinder, again go back to that checkbox, deselect, and then change units to meters and rebuild. Whether this will give me 1000 meter long rod, or the last one is first clear that checkbox of scale values while changing the units, then change units to nanometers, and then again select that checkbox and change units to meter and rebuild. So which option I need to select? So I will just launch the poll question. Please provide your feedback. Yeah, which option that you want to have? So interesting responses that I can see. Okay. I will just keep the poll question open for maybe few more seconds. Means almost it is 2 to 3 more seconds. I will just keep the poll open. Okay, I will close the poll now. Okay, so few people have given selected option as A. A is definitely not correct option. Few of you have also selected B, that is 30% of you, approximately 30%. So well, 30% that B option will also not give you the correct answer, because if you just scale values and then change unit to meter, whatever the you will not end up in having 1000 meters. Just understand the 1 micron to 1000 meter if the scaling will directly work or not. So it has to be either C or D only. So I will not reveal the answer as of now. You can go back and check the same poll question again, because recordings will anyway be shared with you. So if you want to refer to this question again, you can check that question and see that which option is going to give you the required length. It will be either C or D only. So just check that option. Yeah, means many of you have given correct answer as well. So yeah. So now let's look into geometric operations and selections, the next part of the presentation. So with geometry operations, with the core package or with the base package, Yeah, with core package or the base package, you get access to various geometric primitives, Boolean operations, transform features, or you can convert, like you can convert from boundary objects to solid objects, or you can convert from solid to boundary objects as well. If you are having access to CAD import or the labeling for various CAD options, then in that case, you get access to various operations which are required for imported CADs, like repair or defeaturing operations, cap faces, etc. Additional operations that you can get access to also if you are having design module license, wherein you can provide some constraints, dimensions if you are working in 2D modeling environment. With design module, you also get access to some additional CAD building feature as well, that is loft, thicken, mid surface, etc. We will look into this feature shortly. And all the fields, whatever we are using in the operations, can take the expressions based upon the parameters. Like for example, as I was mentioning, you can do the directly geometric parameterization, or at the same time, if you also want to run any optimization solver, just for an example, if you are running some, if you are trying to optimize some distance between two capacitive plates, for example, all of us have seen this parallel plate capacitor, right? And the capacitance of the parallel plate will depend upon the distance between two plates itself. Now in that case, you are having some certain capacitance in mind, that is x picofarad capacitance should be achieved from that particular capacitor design. In that case, you can actually provide while creating the geometry, the gap between these two parallel plates can be represented by some parameter value, and then in that case you can run a optimization solver, in which case you can directly provide that this is the expected capacitance value, and in order to get that expected capacitance value, run the this optimization study in order to extract the required gap between these two parallel plates as well. So such kind of optimization can also be done on these geometric parameters. So now let's look into the few operations. The very first thing is the Boolean operation. While creating any type of complex composite objects, you will need to have the you will need to use the Boolean operations. So just for an example, if this is the end object that we want to have, what one can do is, first of all, one can start with this primitive, the 3D primitives that are shown. The one is block, sphere. Then you can start with one cylinder, and rather than drawing three cylinders, you can directly rotate those cylinders as well in order to get the three different cylinders which are having different axes. Now once these primitives are created, you can apply intersection between these cube and sphere, as well as you can apply union between these three cylinders. You will end up having these two type of different objects. After that, you can apply this difference operation from Boolean and partitions between these two objects, so that you will end up at the object that you wanted to have from this particular geometry sequence. So based upon what your end object is, you will need to see that what kind of primitives that you need to use, and what operation that you need to perform in order to arrive at the required shape. But while doing these Boolean operations, another important thing that to notice is that the tolerance, what tolerance that you are going to provide. There are different options given, that is automatic, that is COMSOL will decide based upon the geometry dimensions that you are having, or you can control that tolerance as well, either relative tolerance or the absolute tolerance. So what do these tolerances mean? The relative tolerance is the absolute repair tolerance divided by the maximum coordinate of the input object itself. Or in other terms, absolute tolerance is equal to relative repair tolerance times the maximum coordinate of your input objects. So for example, if you are having relative repair tolerance, which is given as, let's say, 1e power -6, for example, if you have drawn a cube, and that cube is having dimensions as 1 meter by 1 meter by 1 meter. Okay. Now, rather than drawing that cube closest to the center or the closest to the origin, if you plan to draw that cube let's say the corner point of that cube is written as 1 e power 3, and from there you have directly 1 e power 3 comma 1 e power 3 comma 1 e power 3 kind of corner point dot that you have created used for that particular cube. And in that case, even though your cube dimensions are 1 meter, the absolute tolerance that will be considered will be 1 e power minus 6 into let's say 2 e power minus 3, and the objects entities which are smaller than this entire this absolute tolerance will get merged. So here in this case, as you can see that if this is our starting object, okay. Now if we are having 1 e power minus the gap between these two is 1 e power minus 6, and gap between these two squares is given as 1 e power minus 6. Now if we are having repair tolerance as 1 e power minus 5, in that case you can see that the absolute repair tolerance I am talking about, in that case you can see that this is the gap which got deleted. If you are increasing the tolerance or tightening the tolerance, I would say, you will see that if the tolerance is taken up to 1 e power minus 4, the gap between these two squares will also get removed. The earlier example that I was talking about, that is when you are having a block of 1 meter by 1 meter by 1 meter, and in that case it will depend upon the absolute tolerance will depend upon for any geometry where the geometry has been drawn. That is when you are applying the relative repair tolerance will be multiplied by the maximum coordinate of the object, and based upon that it will decide that whether to merge the entities or not. Hence it is always a good practice to draw your geometry as close as possible to the origin in your geometric plane. If you unnecessarily draw your geometry at some 1,000 kilometer distance from your origin, in that case whatever the tolerances which are getting applied, those will not be the true tolerances, and unnecessarily you will keep wondering that why I am not seeing the features that I want to have in my geometry. Another thing is also that you need to consider whenever you are using any imported geometry in COMSOL, then also it is always a good practice to see that where the geometry is located, and if it is very far from the origin, right, means if it is making some order of magnitude difference, in that case just bring that geometry as close as possible to the origin itself. And for that COMSOL has various commands, that is you can directly move the entire geometry to certain points. That is also possible. The next is from the this Boolean and partition is the partitioning. You can partition objects, domains, faces, etc. And this is typically required. One thing is like as shown over here in order to create the structured meshes, or it could also be that if you are having this as a original geometry, and let's say you want to apply certain type of boundary condition on this curved surface only, and you do not want to apply that same boundary condition on this surface. In that case, you may want to partition that surface. As of now, it is a continuous surface only. So, in those cases, the partition operations could be really very useful. So, for example, one thing as I was mentioning could be like applying the different boundary conditions, or if I directly partition the domain with the extended faces, there are various options available how you can partition it. So here in this case, extended faces option was selected, and from that you can see that earlier it was a single domain only, and then it got means the resulting entity is having three different domains. And now when we are having these three different domains, I can have different types of meshing, or the different meshing scheme can be used in order to create a mesh for this entire geometry object. Now from the transform point of view, there are means few of you were asking earlier that if COMSOL has options to create array, mirror, etc. Yes, COMSOL does have those options. You can have 3D arrays as well as 2D arrays, or there are various techniques with which you can create an array. For example, if you want to create this circular array, you can use this rotate feature so that this entire circular array can be used. Or there is some feature called as move, as I was mentioning earlier. Either you can move that object from one coordinate to other coordinate, or by using this move feature, you can also create a linear array. So based upon various options available under transform, you can also create various types of arrays as you need to have apart from the array feature which is given over here. Now the next part is the conversion. So earlier as we discussed, you can convert geometry objects to solid surfaces, etc. Means for example, if you have created this closed curve, in that case, you can just use convert to solid option and then convert it into a solid surface. Or if you are having this solid surface over here, you can just use convert to surface operation and you can just get a curve out of your solid object. Then there are two different other options are also available, that is thicken operation as well as the mid surface operation. So for many physics you might be having different requirements also. Just for an example, you have got some what I can say, you are having some geometry object like this, which is having a really very means finite thickness. But if you want to use it under shell interfaces, because for various types of physics there are various shell interfaces are available, and in that case you may want to work at the mid surface itself, and in that case you can directly use this mid surface operation and convert this entire that with the geometry which is having finite thickness into a shell type of object. Or if you are having a shell type of object, you can thicken that object. So I will just show you quickly how you can do it. So let's say I'm just 3D only, I am creating it. So in geometry, if I'm having a block, let's say, and I'm going to use dimensions 1 by 1 by 0.01. Sorry. Zero point zero 0.01. Okay. So this is the object that I am having. Now, here in this case, I can go to geometry, then under conversion, you can see there are different options available. So first is mid surface operation that I can say. This is input object. And then in that case, I can just click on build selected. And you can see that it got converted into a surface itself as a with build surface operation. Now, if you are having a surface itself and if you want to create a object, the 3D object, one thing is definitely to create means for such kind of regular type of geometries, regular type of surfaces, you can directly create an extrude operation also. That is, you can just say that, okay, extrude it in a particular direction. But if you are having an object which is something like this, wherein extruding in just one direction will not help you, and that will be like quite tedious process. So in those cases, what you can do is, because in this case you can see that shell will be present at various planes. So how you will be extruding along one direction only. So what you can do is, if you are having such kind of surface object, again you can go to conversion and you can just say thicken. So if I just click on this which surface object, and here I can specify if I want it to be symmetric or if I want to be asymmetric, then in that case it will ask me that what is the upside thickness and the downside thickness, and accordingly it will create a thick objects also out of that. Means the total thickness, if I am just providing 0.01, the one that we had started with, you can see that we got the finite thickness for that particular object. So here in this case, in this particular example, it might seem very simple, but if you are having a complex surface and which is not just a planar surface only, in those cases, definitely the thicken operation would be quite useful. The next is the selections. So means the very first thing could be like, why do we need selections when we are working on COMSOL models? So these selections are typically used, for example, if you want to call same set of boundaries again and again for different boundary conditions, meshing, post-processing. And in those cases, selecting those different boundaries again and again manually might be really very difficult. And in those cases, if you have created a selection which is present here, the selections can be accessed from definitions and selections. If you create those selections over here, in that case, whenever you are applying any boundary condition, I can just say that test 1 as selection that I am creating for this domain. Here in this case, it is just a single domain only. And let's say if I just apply some physics, for example, the heat transfer I am applying. And in that case, under heat transfer, let's say, in this case, again, this is a single domain only. I can just say that rather than having all domains, if I just want to have, means for example, if my geometry is having some 100 odd domains, and out of those 100 domains, I just want to select some 39 domains only. Rather than selecting those 39 domains manually, I can just create a selection for those 39 domains and select them over here. The same time, if I want to select those 39 or the rest of the 61 domains for some different physics interface, then in that case also, I can create a complement of first selection and use them for the other physics interface. So by using these selections, it makes our life easier to access different domains and boundaries. Another advantage of using these selections is that, again, in this case, this domain that I am having over here, it is pretty standard sized domain itself. If it is a very irregular size, irregular shaped domain, or if it is having lots of surfaces, even though it appears to be like just a block only, but there are lots of partitions which are given, and because of that, it is creating lots of surfaces. Rather than selecting those surfaces manually, what one can do is, you can directly have that one input object entity level as domains only. It could be like you can have 4 to 5 domains selected, and the output entities you can have adjacent boundaries. And in that case, it could be interior boundaries, or if you are having two different domains that you are selecting, then the interior boundaries also, exterior boundaries, or you can have interior boundaries also selected. Here in this case, let's say I'm just having exterior boundaries. Now, if I apply any boundary condition, let's say heat flux, in that case, rather than selecting each and every boundary separately, I can select this test one. Please notice that earlier I didn't use these output entities as boundaries. I had kept that output entities as domains only, and hence it was available under domain selection. Now, as I have changed these output entities for that selection as adjacent boundaries, it is available at the boundary condition. And with this, by just making use of, by selecting just one domain, you can see that I can access all the boundaries of that domain. And this is how the selections can be used very effectively also. So there are three different types of selections. The explicit selections means, as I shown you, that wherein you can explicitly select the geometric entity and create selections. Or you can have a coordinate based selection, or you can also create selections based upon the geometric operations. The last bit I will show you during our hands-on session as well. So the coordinate based selection is nothing but that you can create some virtual ball or box, and the entities which are included in that virtual ball or box will be created, will be selected under that particular selection itself. So ball selection window is shown over here, wherein we are showing that what is that virtual ball's radius and what is the center of that ball, and whatever the objects which are included, or the which are in this inside this ball itself, will be selected under the selection that we have created. From the selections from the geometric operations, whenever you are performing any geometric operations, there is an option that if you want to create some selections or not. Again, if you are creating very complex geometry sequence, then rather than creating selections after the geometry is done, so always it's a good practice that if you start creating selections in the very early stage of your geometry building itself. So for example, if this is the geometry that I am having, right? So while creating this first flange itself, I can create selections for that. And in this particular example, we are directly using the rotate feature, means to create this geometry. Then when I'm using that rotate free feature, I can say that contribute to the selection that I have created earlier. So all the boundaries which are resulting from that particular geometry operations will be available under that particular selection itself. So in such cases, you will not have to create any selections. You will have selections separately, or you will not have to put in any extra efforts to create any selections separately. While building the geometry itself, you can say that which selections that you want to create and which geometry operation should contribute to which selections. All these options are also possible. Again, with the selections as well, likewise, you can do different Boolean operations for the geometry. You can perform similar Boolean operations even for the selections. If you have created two selections, you can perform union operation between them, intersection or the difference operation, or the complement, as I was mentioning earlier as well. So with this, before we end this part of the presentation, I would like to launch a second poll question. It is related to the tolerance, because this tolerance concept is quite important to understand which objects or the which features will be retained in your geometry and which features will be removed. So just see that, consider that you are having two squares. Whatever the dimensions that I am going to mention henceforth will be in meters only. Okay. So you are having two squares and both the squares are having same side length as 10 meter. However, the first square is centered at 5 meter, 5 meter, whereas the second square is centered at 15 plus 1 e power minus 4, 5. That is, between these two squares, we are having a gap of 1 e power minus 4. Okay. Now, while performing the Boolean union operation, please listen carefully. If you are performing Boolean union operation, if the relative repair tolerance is mentioned as 1 e power minus 4, what will be the resultant entity? Whether the gap between two squares will be removed, or it will not be removed at all, or the squares will get deleted altogether, or none of the above, something else will happen. So just I will launch the poll question. Please read carefully. If you are having two squares, 10 meter side length of each, the gap between two squares is 1 e power minus 4, and the relative repair tolerance is also 1 e power minus 4. What is going to happen then? I will launch the poll question. Okay. Please provide your feedback. Okay. Many of you are providing the correct answer. That is good to know. Okay. I will just keep the poll open, maybe another 5 seconds or so. Yeah, almost 50% of you have given the correct answer. I'm happy to see that. Just a clue that C and D are incorrect options. You just need to select between A and B, and then accordingly see that what option that you will be selecting. Okay. So I guess people are still voting, providing their feedback. What will be the what this relative repair tolerance is going to do. Okay, I will just close the poll now. Thanks for your feedback. So majority of you have given the correct answer. That is option 1. The gap between these two squares will be removed. Please check. I was mentioning it quite carefully that the side length is given as 10 meters. And hence, in that case, see what will be the absolute repair tolerance that it will be applied. Because here in this case, the relative repair tolerance is 1 e power minus 4. Okay. So the absolute repair tolerance is going to be the maximum coordinate. The maximum coordinate, as you can see over here, roughly is 20 meters, and 20 meters into 1 e power minus 4, that is 2 e power minus 3 is the tolerance which will be applied, and the entities which are smaller than that will get removed, and hence the gap between the two squares will be removed, and those squares will just appear as next to each other, just the touching squares. Okay. At this point, I will just see that if there are any questions left. Okay, just a second. There is one question, how mid surface is different from 2D? In this case, you are working in a 3D environment and you are creating a shell out of that in the 3D environment itself. So, and hence that is how I would say that it is different. There is one more question, can we have move and rotate operation for the array objects? Yes, you can have. You can first, you can move and after that also you can rotate or vice versa. Both the options are available. There is one more question, that why don't we use absolute tolerance? Yes, certainly you can use absolute tolerance. This was just to check that how you can apply for the relative repair tolerance concept as well. You can use either absolute tolerance or you can use the relative repair tolerance also. See, sometimes it may be like a little difficult to know that what should be the absolute tolerance completely. So in that case, just the relative repair tolerance you can apply, or you are very sure that I do not want to have any uh, objects which are smaller than that particular value, then in that case the absolute repair tolerance will also be useful. Okay, so now let's move on. So the last part of the presentation is about the CAD import. So with CAD file import, there are various options available. So whenever you are using this CAD import functionality, this is the window that you will get. And to start with, you can import solids, surfaces, curves, points, or also you can select an option that whether to form solids from the surface objects that you are importing. Here also you can see that there is something called as absolute import tolerance is also provided. Again, the entities, the imported entities which are smaller than this absolute import tolerance will be removed. Then I would say that they will get merged, and that is how this absolute import tolerance works. So here in this case also the associative import is also possible as long as the persistent name of the attribute is present in the CAD file. Means whatever the first CAD file that you are importing, and later if you are modifying the CAD and again importing, and based upon that, if you want to ensure that rest of the assignment done in your model should be intact, in that case always ensure that whatever the attributes that you have you used for the previous import, the geometry import, the same attributes are maintained for the next imports as well. The length units also can be taken from COMSOL or from CAD file as well. Many times just ensure that whenever you are importing a CAD, right, whether the imported CAD is having correct units or not, the correct lengths or not. And for that, the major operation that I had shown you in the earlier part of the presentation, that would be quite useful. So while importing itself, there are certain things will get repaired, like healing the gaps, removing spikes, short edges, etc. based upon the absolute import tolerance that you have provided. At the same time, when you import any geometry, then in that case, it will also show you some warnings as well as the error messages, which will appear right below the import node itself. Here as well, you can generate selections from information in the CAD files, like the different selections for the materials, colors, layers, etc. All those things are also possible. So the automatic repair, as I was mentioning, that is dependent upon the absolute repair tolerance that you are providing. With that, it will be removing these short edges, small faces, or the sliver faces also. For example, this is the entity that you are, or this is the geometric object that you are importing in COMSOL. And let's say this is the spike that you are having. Now, if the absolute import tolerance is defined as 1 e power minus 5, that's what the tolerance that we are having. Then in that case, you can see that as the entity which is shown over here is smaller than the absolute import tolerance, and hence that spike will be removed, and this is the end object that you will be having for the analysis. Now from the interfacing products functionality, as mentioned earlier, either you can create geometries using COMSOL CAD tools, or you can import the finalized geometries using CAD import module or the design module, or if you are having access to Livelink for any CAD products. But if you are having access to design modules or any Livelink products, you get access to additional functionalities as well. So let's see what are what all those. So with CAD import, you get access to repair and defeaturing. You get access to cap faces, etc. Means I will show you that how these, why these options are required in order to get a smooth geometry object for the analysis. You can also have different type of CAD file export as well. This is available with the CAD import module. However, if you are having access to design module, you get access to the CAD import module functionality. In addition to that, you get access to various additional features as well, like filleting, 3D filleting. 2D filleting is anyway possible with the base package itself, but if you want to have a 3D filleting, then that is possible with design module, that chamfer, loft. Loft is nothing but, for example, you are much aware of the extrude operation by now. But if you are having two irregular surfaces and if you want to just create a solid object between these two surfaces, which are these two surfaces, in that case you can directly use a loft operation, and you can say that just the geometry should be grown from the one surface to the another surface, the mid surface and thicken objects that we have seen. This is about the design module. If you are having access to the Livelink products, again here also you get access to all the features which are available with CAD import module. In addition to that, you also get access to the bidirectional interface for CAD data exchange between COMSOL and that other parent CAD software. Also, in addition to all these three different modules, or these three different sets of modules, I will say, because Livelink products itself is not a one module. There are different Livelink for AutoCAD, SolidWorks, etc. modules available. In addition to all these these modules, we are also having ECAD import module, wherein you can import your PCB layouts into COMSOL. It could be like ODB++ or GDS2 type of files. And once you import those, it could be like the multi-layer PCB files also, PCB layouts also. And then you can create the 3D PCB layouts from that. That is, if you want to have a different thicknesses given for the each layer or so, that is also possible. Just bit about the Livelink interfaces. As mentioned, it is a bidirectional interface between COMSOL and the parent CAD software to synchronize the design. So here in this case, you can transfer parameters to CAD program to modify the design itself, and then updated geometry can be sent back to COMSOL multiphysics also. Means just for an example, if you are running some optimization study or so, right, then based upon the solver, your geometry should get updated. Then that geometric parameter will have to be sent back to the CAD program. CAD program will rebuild the geometry and will send that updated geometry back to COMSOL multiphysics. This is for Livelink. But if you are using even COMSOL's native CAD tools, then also this geometric parameter optimization that can also be done. With Livelink interface, it will also ensure that associative transfer of geometry is maintained. Maintained for your analysis. So now let's look into few defeaturing and repair techniques as well. So when you are bringing any imported CAD into COMSOL, one need to ensure that you are getting a good quality CAD. Good quality in the sense it is not having unnecessary details present in the geometry that you are importing. But the quality will also depend upon various things. The original format that you are importing. Just for an example, when you are importing geometry, it is recommended that if you are having if you want to work on any 3D solid modeling, then in that case, do not import any STL type of file, which is just a shell file, and do not try to create a 3D object out of that. Though it is possible to create such kind of 3D thick objects from that, the quality of that CAD will be really very poor. So it is, if you are working on shells, then definitely the STL file format will be appropriate. But if you know that if you need to work on the 3D solid modeling only, then rather than using STL format, use any other parasolid format like step file or step file, etc. file format that you can have. Then the quality of the geometry will also depend upon who is creating the geometry and whether which software that has been used to create the geometry. If it is experienced designer, definitely he or she will ensure that the unnecessary details are not present in the CAD, or the number of operations while creating the original CAD are kept to minimum in order to ensure that not unnecessary edges, surfaces or domains are getting created. Then the quality of the translation tools and the number of times the geometry has been translated. These two are important. Means, for example, translation is nothing but you are using some one CAD software, let's say some SolidWorks or AutoCAD, and you want to export that geometry which is compatible with COMSOL's CAD format. It is available on our website also, that what are the different formats are available. But typically saying parasolid formats are possible with CAD import itself. Now, in that case, you need to see that which format that you are exporting it to, and at the same time, how many times you are translating that. Means, for example, if you want to get the final file in .stp format, and before getting into .stp format, first of all, let's say if you are exporting it from AutoCAD, you are exporting it in DWG format, and from DWG again you are converting it into stp format. That means you have translated that geometry twice, and with each translation, based upon the tolerances which are used to translate that geometry, the errors will be introduced, and the final geometry which you are going to input within COMSOL might be having some unnecessary errors as well, which might not have present if you have directly exported the original geometry into stp file itself. So always another suggestion is that whichever the CAD software that you are using, try to export that in export your CAD file into the native format of that particular software itself in order to reduce the translation errors. So from the defeaturing point of view, the very first thing is that the cap faces. So for example, if you are having this kind of geometry which has been imported over here, and wherein we are having a gas channels, you might be seeing those gas channels, like you can just imagine as grooves which are present over here. But from the modeling point of view, even though these are grooves, you can see that these are not the closed channels, and as they are not the closed channels, you will not be able to solve any flow inside those channels, because you need to have a solid mesh inside those channels. And in those cases, you can use this cap faces operation in order to close those channels. If you want to remove those surfaces, you can use delete entities, or if you want to remove the channels itself altogether, you can use this delete faces operation. It will be clear in the next slide. So for example, whenever you are using delete entities, so let's say you have used these faces, first of all you have capped these faces, and then by using this delete entities operation, you will see that the extra faces will get removed, but the grooves will remain on the original geometry itself. Whereas rather than using that delete entities, if you use this delete faces feature, it will heal the gaps which are created while when you are removing those faces itself. Means, for example, when we are using this delete faces operation, it will not just delete the faces, but you can see that the underlying those channels were also removed, or they were healed, and you ended up with the complete solid object only. So based upon again your requirement, whether you want to have that grooves to be maintained in your final object, or if you want to have a complete solid object, one can decide that what option to be selected. Then for the imported geometry, there are certain other options. Again, these are like how you can improve your CAD for the further modeling, because we do not want to have unnecessary details present in your CAD, which will unnecessarily lead to extra number of mesh elements, extra surfaces, because of which your model become unnecessarily heavy also. So the another option is that this delete holes option. So again, if this is the original object that you have imported, right, based upon that delete holes option, means what radius that you are providing, you can see that various holes or the various circles will get selected, and the end object will altogether be different, again based upon what radius that you are using. So in one case you can see that this internal hole is getting just closed, and this is the end object, or this is the end object that you are getting. Whereas if you are increasing the radius of that hole, that is that delete holes which are smaller than this radius, the holes which are having radius smaller than this which is specified, in that case you can see this is the end object that we are having. So again, based upon which entities that you want to remove, which details that you want to remove, you need to specify the you need to use the features appropriately. Even though you are using delete holes, what radius that you want to use, because what features that you want to get merged, what features that you want to get healed, accordingly you need to specify the details of the various operations that you are using. Another operation is like the detached faces operation as well. Now the detached faces operation is typically useful, means for example this is the imported object that you are having, though here in this case we are having a solid object inside that. The way that the object has been created is such that you are not able to, this is not the closed object, and hence you are not able to apply any different type of material, or you are not able to create any channel inside that. In that case, if you just select this as a detached faces operation, right, and select these surfaces under detached faces, it will create separate domain. That is, the outer part will be the separate domain, this inner part will be the separate domain, and hence you can apply this various types, various material properties or the domains or the boundary condition as well. Next, apart from these defeaturing operations, you also get access to these virtual geometry operations also, which complements the CAD repair and defeaturing. But the obvious question will be like, what is the difference between CAD repair and the defeaturing? So the virtual geometry operations will be done after the finalization, that is the form union or the form assembly is done. Whereas the CAD repair operations, CAD repair and defeaturing operations will be done before the finalization step is approached. So if you see in the geometry sequence itself, right, whenever you are using any CAD repair operations, they will appear before the finalization node, and the virtual geometry operations will appear after the finalization node. And hence the virtual geometry operations will ensure that how the measure is going to see your geometry, that is, it will keep the underlying surface curvatures intact, but at the same time it will hide it from the measure itself. And in those cases, measure will not unnecessarily create a really very refined mesh over there. So for example, if this is the original geometry that you are having, rather than removing these small the sliver faces over here, what we have done, we have used these virtual geometry operations. So here you can see that the curvature of that surface is maintained, but just the sliver faces thickness, which wherein otherwise the very fine mesh would have been created, that has been hidden from the measure itself. So it essentially it hides the geometry features from the measure, and it can be used to get rid of various different small details from the imported CAD, like sliver faces, short edges, small faces, etc. All these various options are available under the virtual geometry operations as well. So this was about today's session, that wherein we have seen how you can use different operations, the finalization methods, then how you can handle the geometry sequences, how you can work with imported CAD as well, and few options in order to repair the CAD also. So with this, we will just have our hands-on session to start with. In this hands-on session, we are going to create a CAD for this disk stack heatsink. This is the geometry that we are looking after. So this example model is available under our application database as well as on in the application gallery on www.comsol.com. So after the session is done, if you want, you can just search for this disk stack heatsink, and you will get this entire model wherein all the geometry steps. And here in this case, we are not going to use the complete parameterization, but the model file or the step-by-step instructions what we are having in our website, they are having the complete geometric parameterization done for this particular model. So here in this case, the physics is pretty simple, though we are not going to build any physics. I would like to discuss why we are working on this problem. So this is particularly a heat sink design in order to understand that how you can increase the efficiency of this heat sink itself. So that's to start with, we are having just the heat sink where you can see we are having just this thin plate which is kept on top of this central IC, and then we can see that how much is the heat dissipation occurring in this circuit board. The next is like we have also included this stack heat sink over here, and with that we were trying to understand that how much is the heat dissipation with those the disk stack. Here in this case, the discs that you can see, these are the 2D discs that we are going to use over here. So this particular example model will show you that first of all how you can use various array features, copy features, etc., as well as how you can create such kind of 2D objects in 3D. And I will also show you how you can create geometric selections which will be useful. In this particular example model, from the physics point of view, we are using this shell interface for the heat transfer as well, the layered shell interface for the heat transfer in order to account for the heat transfer through this disk heat sink also. So if you are having COMSOL open, please switch to COMSOL window now. Meanwhile, while you are opening it, I will just show you that where that example is present. If you directly go to this application library and just start typing disk stack, you will see that under heat transfer, you will find that example. Under heat transfer module, this is thermal contact and friction. You will see this disk stack heat sink. After the session is over, you can definitely go back and check. The PDF is also given wherein all the step-by-step instructions are given. So if at all, if you miss any instruction today, please don't worry, the instructions are present. So now I'm just starting with empty model, that is the new model, then the model wizard, then the space dimension I'm going to select as 3D, and here in this case I'm not going to use any physics at all, so just click on done. Okay, as mentioned by Uttam in previous session, at any point of time you can click on this reset desktop window in order to get the standard COMSOL graphical user interface. So this is the CAD that we are going to create now. To start with, the geometry that we are going to create is in mm dimension. So the length unit I am going to change to mm. Okay. Now once it is changed to mm, first we will draw that circuit board block itself. So right click on geometry and select block. So right click on geometry and select block. So here in this case, I'm just directly going to provide width, depth and height information. Width is 150 mm, depth is 150 mm and height is 3 mm. So block 1, 150, 150 and 3. And the corner point that I'm going to provide over here is minus 75, then y equal to minus 75 and z equal to minus 3. Okay. So this is how the first block is created. So this is the block that I have created. The next block that I'm going to create is for the central IC now. Either you can add new block by right clicking on geometry 1, or you can right click on block 1 and select duplicate. Okay. So here in this case, I have just added a second block. The width for the second block is 50 mm. Depth is going to be 50 mm. And the thickness I am going to keep as 3 mm only. The corner position that I am going to have is minus 25, comma minus 25, comma 0. Sorry, 25, comma 0. So this is the central block that we have drawn. Same way, you can just right click on the next IC that we want to draw. You can just right click on this block 2 and duplicate it. First, we will draw the basic blocks that are needed, and after that, I will show you how you can use different transform operations. So I just added block 3, and this is for IC. So I'm just going to use width as 20, depth as 15, and height as 3 only. The corner position I'm going to use as minus 60, comma minus 60, comma 0. Okay, so this is the IC that I have created. Now, as you can see over here, this is the IC that the corner IC that we have created. Okay, this one. Now we want to create the same set of ICs in Y direction as well as in X direction as well. So for that, one can use copy feature, and in that copy we can say that how many elements that we need in Y direction and how many number of elements we need in X direction as well. So for that, right click on geometry. Then here in this case, transform, you can see this copy feature. Select copy feature. We want to create copies of this IC. So just take your mouse over here and select it once it is highlighted. Now we will need to provide the displacement vector. At the same time, it is the keep input object is checked. Please ensure that, because if you remove this keep input object, then in that case the original IC will get removed. You will create copies of that IC, but this original block will be removed. Okay, so now we will have to provide the displacement vector as well. Okay, so now here for the displacement vector, as you can see, we are having few ICs in this Y direction, for which the X coordinate is not changed. And for that, what we are going to do is, we will be just providing the displacement vector as 0, 0, 0 space, 0 space, 0 space, 0. That is the 4 zeros that I am providing. That is the 4 additional ICs that I am going to provide over here. Then the next, this is just to show you that how you can specify a range also. That is 30. Start with 30. The step size is 30 and stop is 60. Add, and the next displacement is 30. So the same object I want to get repeated at different displacement. The first 4 are the just 0, 0, 0 only, and next are the I am specifying some displacement in the X direction. However, as of now, I am not providing any Y displacement or the Z displacement. So even if I build it here, you will see that just the 2 ICs are provided over here. I did not get anything created in the Y direction at all. So here in this case, what I need to provide is the Y directional displacement as well. So in the Y directional displacement vector, I am going to provide, start with range as 25, step size is 25, and it should stop at 100. So here add, I can just mention, not add, I just want to remove it. Yeah, replace you can have that, start with these vectors, then provide 0, 0 and 100. If I click on build selected, you will see that these are the required objects that we obtained, because unless until you provide x and y vector completely, you will not be getting array in the y direction as well. So that's what it was lacking. Yeah, so how the range is defined. Okay, so here in this case, I started with, first of all, selected this block 3. Then after that, ensure that you are having this keep input objects checkbox is selected. Once it is done, I need to provide the displacement vector. That is, when I am creating a copy of this input object, what should be the displacement? That is, in the x direction, what should be the displacement? And in the y direction, what should be the displacement? Now, in the complete this object that I have created, the copy feature, you can see that there are 4 more ICs which are created with same x coordinate, but we are having y displacement, and hence first I have provided x equal to 0, 0, 0, 0, and after that I have provided x equal to this 30, 30 as a range, and the next displacement vector as 30 as well. So this is how we have created all these ICs. Means first of all, in the x displacement that has been given, later I have given the y displacement as well, in order to create the ICs which are present on this PCB. The next is we need to provide the next block of IC to create IC. So right click on geometry and select block. The width I'm going to provide is 15 mm. Depth is 40 mm. And height is 3 mm. 15, 40 and 30. Sorry, 15, 40 and 3. Whereas the corner points I'm going to provide as x equal to 40, y equal to minus 50 and 0. So this is one IC that I have created. So 15, 40 and 3 are the width, depth and height. And the corner point that I am having is x equal to 40, y equal to minus 50 and z equal to 0. Just a second, there is a question. Yeah, on build selected, incompatible length of displacement vector is coming. Please check that you have provided the complete displacement vector as I have mentioned over here. That is 0, 0, 0, 0, 4 zeros, then range 30, 30, 60 and 30. This is the x displacement vector, and the y displacement vector corresponding to the length of the x displacement vector, you have provided the y displacement vector as well. That is range equal to 25, 25, 100. That is, you just need to click on the range, start, step and stop. After that, write 0 space 0 space 100. So with that, you should be able to get rid of that error. Yeah, one question is that which corner point it is showing. So the corner point that we are considering, this is the corner point that we are considering, and accordingly it is getting built. So for this object, this corner point, this object, this is the corner point that we are considering. This object, this is the corner point that we are considering. If you have missed any step, anyway, this the recordings of this session will be shared with you. So you can also again watch that recording and you can repeat the step. Okay, so the block 4 is created. Then I will just right click on geometry and create a copy. That is geometry, transform and copy. Now here in this case, I am going to select this block 4. Again, keep input object should be provided. Here in this case, you can see we just need one more IC over here. So what I am going to do is that IC with some Y displacement. So just Y displacement equal to 50 I am going to provide and click on build selected. So this is how you will be creating ICs. Yeah, block 4 step. Someone is asking me to repeat. So in block 4 I have created this block 4 as 15